This is video 10.3, which deals with elastic collisions in one dimension. We learned about collisions in general in the previous video. We said that momentum was conserved in collisions, and we also said that there are three kinds of collisions. Well, really two kinds. There's elastic collisions in which energy is conserved, and there are inelastic collisions in which energy is not conserved. And today we're looking at elastic collisions. So we know that both energy and momentum are conserved, which means that we can now write two equations when we solve these problems, and that means we can solve for two unknowns. So the math gets a little bit hairy sometimes, but if you're okay with algebra, then elastic collisions are really not any more difficult than inelastic ones. So what you do is you write down one for momentum. So let's say you have two particles in the collision. You have m1 v1I, so that's the initial velocity of particle 1, plus m2 v2I, the initial velocity of particle 2, equals m1 v1f plus m2 v2f, that's the final velocity of particle 2. And that's the kind of thing that we did in the previous problems. But now we'll also write one for energy, because if we're told that the collision is elastic, we know that the initial kinetic energy is equal to the final kinetic energy. So m1 v1I squared plus 1/2 m2 v2I squared equals the final kinetic energy 1/2 v1f squared plus 1/2 m2 v2f squared. And typically you'd know there are, let's see, 1, 2, 3, 4. There are 6 different variables in these equations. Typically you would know 4 of them and be asked to find the other 2. And then you'd solve them simultaneously. And you've got 2 equations. Unfortunately, one of them is not linear because all the v terms are squared in the energy equation, which means that you can't use linear combination, you have to use substitution, and it's kind of a pain sometimes. So you'll often want to plug in numbers relatively early with these, just to make the math, or make the algebra a little bit better. And so here's an example. Let's say we have an air track. We have a cart of 340 grams mass, initial speed 1.2 meters per second, and it collides with a stationary cart of unknown mass. The first cart then continues in its original direction at 0.66 meters per second. What's the mass of the second cart? And part B of the problem will also want to find the velocity of the second cart after the collision. So the first thing, let's draw a picture. Initially you have a cart of unknown mass m, also this cart of mass, I'll call that m1 and m2, and this one has a velocity of vi, and this one's not moving. Now after the collision, we know that m1 continues in its original direction at speed vf, and we know that m2 starts moving. We don't know how fast though, but we can say that it's moving in that direction. I'll just call v the unknown velocity there. And we know that v will be larger than vf because m2 cannot have passed through m1. It's very important. And so now we will write down 2 equations, one for conservation of momentum. And what that says is that the initial momentum, m1 vi, m2 isn't moving so it has no momentum, equals the final momentum, m1 vf plus m2 v. And at this point I'm going to plug in numbers for m1, vi, and vf, and we'll find out that m2 v is equal to 0.1836 kilogram meters per second. Now we're also going to apply conservation of energy. So we'll say that the initial kinetic energy, 1/2 m1 vi squared, equals the final kinetic energy, 1/2 m1 vf squared, plus 1/2 m2 v squared. And we will immediately multiply the entire equation by 2 to make things a little bit easier. And we're also going to plug in numbers and find that m2 v squared is equal to 0.3415 joules. So we've plugged in numbers early, and now we have two equations, and this actually ends up being pretty easy to solve. Because if m2v is equal to this, m2v squared is equal to that, well, we say that, well, m2v is just m2v squared is just m2v times v. And so this becomes 0.1836 times v equals 0.3415. And then we find the velocity of the second cart is 1.86 meters per second. That's the answer to part B, which is on the next slide, but we can get it at this point. And then we'll substitute that back into this equation and find that m2 equals 0.099 kilograms, or 99 grams. Now let's ask ourselves, does this make sense? And the first thing we notice is that the final velocity v is in fact larger than vf, which is what we wanted. The other thing we can see is that the mass of glider 2 is smaller than the mass of glider 1 by a pretty large margin. That's also something we'd expect because small things tend to bounce off with high speeds when they hit big things. And so m2 is going to bounce off with a relatively high speed, and that will change the velocity of m1, but it will keep moving. It's like if you throw a baseball at a car. Don't do this, by the way. The baseball will bounce off, the car will keep going just a little tiny bit slower than it was before. And you will or have done some experiments, I don't know at this point what the order is, where you will verify this. And we said we found the speed of the second cart already, blah, 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 blah. For tomorrow, I'd like you to work problem 35, not a question, but a problem where you have to apply the idea of elastic collisions.